Hey folks, Professor Gray here, ready to talk to you about disjoint events and other probability rules. When flipping a coin, getting heads and getting tails are disjoint events. So what does that mean? What does disjoint mean? Well, disjoint events cannot occur at the same time. They're mutually exclusive. At the bottom of this slide, you have two Venn diagrams. On the left is the Venn diagram for events that are not disjoint. You have event A and event B, and then event A and B can overlap. The Venn diagram for disjoint events on the right, event A and event B do not overlap, cannot happen at the same time. They are disjoint. So instead of a joint effort, you work together with someone, disjoint, they are separate. Compound events combine two or more simple events. For example, you roll a six-sided die and get a 1 or a 6. Those are compound events. In notation, probability of A or B is the probability that in a single trial, event A occurs, or event B occurs, or they both happen at the same time. So now we've talked about compound events and disjoint events, we can talk about the addition rule. The addition rule allows you to find the probability of an event or another event happening or them happening at the same time. Probability of A or B. It is the probability of A or B equals the probability of A plus the probability of B minus the probability that A and B happen together. That's the addition part. Probability of A and B denotes the probability that they both happen at the same time, and if A and B are disjoint, then the probability of A and B happening at the same time is 0. So we can omit the last part, the subtraction. Let's do a few examples. Number 16. What's the probability of rolling a 1 or a 6 on a single roll of a six-sided die? Number 16. So notation, probability, x equals 1 or 6. Well, how many sides have a 1 on them? A six-sided die, only one side has a 1, so that'd be 1 over 6, or tells me that I should add probability of getting a 6. There's only one side that has a 6. So 1 over 6. Now, the probability of them happening at the same time. Is it possible to roll a die and get a 1 and a 6 at the same time? Well, no, the answer is no, so that's minus 0. This is the principle of inclusion and exclusion. So 1 6 plus 1 6 is 2 out of 6, which is 1/3. Or is a decimal 0.3 repeating? Number 17. What's the probability of rolling a 12-sided die and getting a number greater than 3 or less than 2? So probability that x is greater than 3 or x is less than 2. So how many ways can we get a number greater than 3? Well, there are 9 numbers on a 12-sided die out of 12 that are greater than 3. The or tells me I should add, use the addition rule. Less than 2. Well, there's only one number less than 2 on a 12-sided die. That would be 1. And can I get a number greater than 3 and less than 2 at the same time? No, this is impossible. So 9 plus 1 is 10 out of 12, which is 5 out of 6, or its decimal equivalent. Number 18. What's the probability of rolling a 4 or an even number on a single roll of an 8-sided die? This is the probability x equals 4, or even. Well, there's only one side of an 8-sided die that has a 4, so that's 1/8. How many sides have an even number on them? I'll add those in. That would be 2, 4, 6, and 8. So that's 4 sides out of 8. And is it possible to get a 4 and an even number at the same time? Oh yes, it sure is. How many ways can you get a 4 and an even number at the same time? Only one side, the 4, gives you that. So subtract that back out. The reason we subtract it back out is because this one side of the 1/8 is the 4. And one of the 4 even sides is also the 4. Well, there's only one 4 on the die. So I have double counted it. I counted it once, counted it again, subtracted out one time, and now I've only counted it once. Counted it twice, take out once, now I've only counted it one time. I add those together, I get 4/8 or 1/2. So we're avoiding double counting. Number 19, probability of picking a card from a standard deck and getting a heart or an ace. So probability of a heart or an ace. How many hearts are there in a standard deck? That's 13 out of 52. Or tells me to add, how many aces are there in a standard deck? That would be 4 out of 52. Oh, my mistake, I have a typo there. First denominator is 52. There we go. Now, is it possible to get a heart and an ace at the same time? Oh yes, it is. How many ways can that happen, or how many cards does that happen on? Well, only one of them. That would be the ace of hearts. That's a heart and an ace at the same time. So subtract that, because one of these 13 hearts is the ace of hearts. One of these 4 aces is the ace of hearts. I have double counted it. Subtracted out once. Now I've only counted it once. Alright, well, if I take a look on my calculator and use some parentheses, I can find this amount. And now I have the decimal equivalent. I'm going to round it to 4 places, 0.3077. That's my answer. That's how I can use the addition rule to find probabilities of events involving the word or. Well, now let's talk about independent events. 2 events A and B are independent if the occurrence of one does not affect the probability of the other occurring. They're independent, they stand alone. If A and B are not independent, then they are dependent. Let's look at some examples. Are A and B independent or dependent in these scenarios? Number 20. Event A. A month is randomly selected and ripped from a calendar. Event B. Another month is randomly selected and ripped from the same calendar. Independent or dependent? Well, if in event A I happen to select, let's say February, then in event B I can't select February again. So whatever happens in A affects B. Those are dependent events. Number 21. A baby girl is born. A second baby girl is born into a different family. Well, event A does not cause or change the probability of event B. So these are independent events. Number 22, you randomly select a chocolate from a box and you eat it. Event B, you randomly select another chocolate from the same box. Well, if you're dealing with the same box and you've taken a chocolate out and eaten it, it is impossible for you to select the same chocolate again. So what happens in A affects B. Those are dependent events. Conditional probability accounts for when events are dependent. It's used when things are selected without replacement or when other events are given. Without replacement means you take something but you do not put it back. You did not replace it. Given means that you are assuming a particular condition. Notation-wise, probability of B given A is shown by P of B, vertical line A. And with the formula, that's equal to the probability of A and B occurring divided by the probability of A occurring. For the most part, we will not rely upon the formula. We'll use some logic in order to find conditional probability. Conditional probability is used in the multiplication rule, which, spoiler alert, involves multiplication. The probability of A and B is the probability that A occurs in a first trial and event B occurs in a second trial. It's found by multiplying the probability of A times the probability of B, given the fact that A has already occurred. Now, if A and B are independent, then it doesn't matter that A has already occurred, and you'll multiply the probability of A times the probability of B. Let's do a few examples. Number 23. Says, what's the probability of rolling a 6-sided die twice and getting a 3 both times? So that's the probability that x equals a 6 and, a 3 actually. Strike that. Probability that x equals 3 and 3. Well, the first time I roll, how many sides have a 3 on them? One of them out of 6. And I'm going to use the multiplication rule. There's one side that has a 3 on it for the second roll. Does that change for the second roll? No. So 1 out of 6. When I multiply fractions, I multiply the top, multiply the bottom, I get 1/36 or its decimal equivalent. Number 24. What's the probability of drawing a jack, queen, and king from a deck of cards in that order with replacement? Probability of jack and queen and king. When I draw the first time, there are 4 jacks out of 52 cards, and use multiplication rule. When I draw the second time, well, with replacement means that I put my jack back into the deck and it was reshuffled. So there are still 4 queens out of 52 cards. I put that queen back, and then there are 4 kings still out of 52 cards. Let's find the decimal equivalent of that. That would be 4 out of 52 cubed. Well, the calculator shows us some scientific notation with that answer. It's actually 4.6 times 10 to the negative 4th. That's what the E negative 4 means. So I'll take the decimal and move it 4 places to the left. That gives me approximately 0.2346, which is 0.0005 when it's rounded to 4 places. So it's a very unlikely event. number 25 is similar but with one minor change. Find the probability of getting a jack and a queen and a king in that order. This time without replacement, so I don't put the cards back. The first time I draw, there are 4 jacks and 52 cards. That's the same. Now assume that you got a jack. Without replacement means you don't put it back. There are now 4 queens, but 51 cards remain in the deck. You take that card and hang on to it. There are 4 kings to get, but now there are only 50 cards in the deck. So let's find that decimal equivalent. If I use parentheses, I can do that in the calculator like so. And I get something similar to what I got in number 24. I get 4.8 times 10 to the negative 4th, which is a little bit bigger than the answer in number 24. So not putting the cards back helps your chances. When I move the decimal over, I still get 0.0005, which is extremely rare. Those are my probabilities. Number 26. Find the probability of pulling a red ball and a yellow from a bag with 3 reds, 4 yellows, and 5 greens without replacement. So you don't put them back in. Probability of red and yellow. So the first time you pick, there are 3 reds, and the total number of balls is 12. 3 plus 4 plus 5. And you're going to pick again. You keep your red ball, assume you got a red. There are 4 yellows, and now there are 11 balls left in the bag. Well, let's find the decimal equivalent of that. All right, the answer is 0.0909 approximately. So those are my answers using the multiplication rule, and I just adjust as I go for any conditional probability. I didn't have a whole lot to worry about in 23 and 24. Didn't have any conditional probability to worry about. In 25 and 26, I had to adjust my totals as I went to reflect the fact that I was not replacing items. In the next video, we'll talk about contingency tables and how to find probabilities using them.